Welcome back. In the second part of this section, we're now going to introduce the first derivative test, which builds on what we did with increasing and decreasing intervals just moments ago. So we've got ourselves a function and we've found ourselves a critical number. So x equals c is a critical number for our function. That function is continuous on some open interval containing c. So we know definitely that means that x equals c is not a hole. X equals c is not the location of a vertical asymptote. The function is differentiable on the interval, maybe not at c itself. So maybe we've got a vertical tangent line. That might be a thing. But our function is definitely continuous, and we've got a critical number at c. So the idea here is to ask ourselves what's happening with intervals. Are we increasing or decreasing or what on either side of c? So if we're thinking about having some sort of a function and we know what's happening at x equals c, if it turns out that we were decreasing before c, so if f prime was negative before, so if we decreased, and then if f prime was positive after c, in other words, if it increases after c, well then that must mean that c must be the location of a minimum. And the reverse would also be kind of a nice little thing to note, that if you had c and if you had before it the derivative was positive, in other words you were increasing, and after it the derivative was negative, you were decreasing, well then that must mean that at c you've got a relative maximum. And if you're doing the same thing on either side of c, if we're going from increasing to increasing or decreasing to decreasing, then that's not a relative max or a relative minimum. So for example, you might have something like our graph y equals x cubed, and you can check to see that for y equals x cubed, that its derivative shows that there should be a critical number at 0. And it increases before 0 and then it increases after 0, and that's why it's 0 for y equals x cubed. Even though it's a critical number, it's not a maximum, it's also not a minimum. So that kind of gives us our idea of how we're going to carry out our first derivative test, how we're going to find if something is a maximum or a minimum. We're going to begin kind of like we did before, and you might notice that this is the same problem that we did before. So I'm going to rely on some of my earlier work to speed through this first example. We would do the same thing we did before of finding all of our critical numbers and finding out what's happening on our interval at all of those critical numbers. So previously we found that we had over the interval from 0 to 2 pi critical numbers at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And we also found that it was increasing, followed by decreasing, followed by increasing, followed by decreasing, and followed by increasing. So now we can say, well, number one, we have a continuous function. That was one of the things that we needed to have for the first derivative test. We needed to know where the critical numbers were, and it needed to be continuous at that critical number. And for sure, we're continuous at all of those points. And then depending on what's happening for increasing or decreasing on either side, we can classify each of those critical numbers as being the location of a minimum or a maximum. So if we're thinking first about x equals pi over 4, or theta equals pi over 4 rather, our graph is going from increasing to decreasing, which means that there should be a relative max at pi over 4. At 3 pi over 4, we were decreasing before it, then we're increasing after it. That means at 3 pi over 4, that should be a relative minimum. And then I can do the similar sort of thing for the other two critical numbers. For 5 pi over 4, we increase followed by decreasing, so that's a relative maximum. And then finally at 7 pi over 4, we went from decreasing followed by increasing. That's the location then of a relative minimum. Okay, so that's essentially it. So you'll notice that the first derivative test is actually just only one stage further from what we've already done. So we find our critical numbers, we find where things are increasing and decreasing, and then now the first derivative test is just using that to draw conclusions. So let's do another one here. We've got g of x. This is a product, so we're going to need to look at product rule when we find our derivative. Before I do that, though, I know as far as this function goes, it's continuous everywhere. I mean, this is some sort of a polynomial, so I don't have to worry about any places where it's not defined. So that's kind of good to think about at the start. And now let's find our derivative. And so here we go. First thing as it is, derivative of the second. So power rule says that the 2 will come down, the power will get reduced by 1, and chain rule for the derivative of the inside, derivative of x minus 2, that's 1. Plus the second thing as it is, times the derivative of the first thing, the derivative of x squared minus 1, that is 2x. I notice I've got a 2 that's a common factor in both terms, and I've got an x minus 2 that's a common factor in both terms. So I'll factor that out. And that leaves me in the first term, I've got an x squared minus 1 hanging around. And in the second term, I have the x minus 2 times the x hanging around. And if I were to clean that up, that would give me 2x squared. Oh, sorry, that would give me 2x squared minus 2x minus 1. Okay, so we have found our first derivative. Our first derivative is nice and continuous. We don't have any places where g prime is not defined. So for critical numbers, we would have to find where is g prime equal to 0. It's already been factored for us, so there's 2 places to consider. One of them is x minus 2 being equal to 0, which happens to be when x is 2. The other is when 2x squared minus 2x minus 1 is equal to 0. That doesn't factor very nicely. So if you use the quadratic formula to solve this, you find that there's 2 solutions. One of them is at 1 plus root of 3 over 2, and the other one is at 1 minus root 3 over 2. 1 plus root 3 over 2, just as far as a decimal number goes, that's about 1.36-ish. And 1 minus root 3 over 2 as a decimal number, that's about negative 0.36. We need to know that, of course, because we want to be able to put our numbers in order, and we also want to make wise choices about which numbers to select for our test points. So for our 3 critical numbers that we have negative 0.36-ish, positive 1.36 around, and then 2. So putting them in order from smallest to largest, we'll have that 1 minus root 3 over 2. That's the smallest one. Then the next one up is the 1 plus root 3 over 2. And then the next one up after that is 2. And now let's figure out what we are going to choose for our x values. So this x value that we have here is a negative 0.36 thereabouts. So something smaller than that might be negative 1. Between negative 0.36 and 1.36, 0 would be a convenient choice, or 1. I'm going to choose 0. And then between 1.36 thereabouts and 2, I guess 1.5 would be a good choice there. And then for larger than 2, I will choose 3. And now I'll put them all into my derivative. And when I did this earlier, g prime of 1 came out to be negative 18. So we are decreasing in that interval. G prime of 0 turned out to be positive 4, so we are increasing in that interval. At 1.5, the derivative had a value of negative 0.5. So negative, that means you're decreasing. And then at x equals 3, the derivative was 22. So that's positive, we are increasing. So now, for our three critical numbers that we have, we can now say, courtesy of the first derivative test, at the first critical number, we went from decreasing to increasing. So, from the second critical number, we went from increasing to decreasing. And at the third critical number, we went from decreasing to increasing, which means, looks like we have two relative minima. So one of them is at 1 minus root 3 over 2, and the other one is at positive 2. And for the relative max, we happen to have one at x being 1 plus root 3 over 2. Okay, one more to look at here. This one's a quotient, so a little quotient rule fun. Right away, I can say at the top that I know that this function has a vertical asymptote t equals -1. So in other words, functions not defined at -1, which also means that -1 will be a critical number because there will be no derivative at -1. But we'll also have to think about that carefully as we get to the end of our work here. So let's start off with finding our derivative. So the bottom will get squared. Bottom comes up. Derivative of the top, and for that, chain rule. First, power rule for squared. Power comes down, power is reduced by 1. And derivative of the inside, derivative of t, that's just 1. And derivative of 3 is 0. Okay, so minus, and then the top as it is, t minus 3 squared, times the derivative of the bottom. The derivative of t plus 1 is 1 plus 0, which is just 1. I notice in the top I have a t minus 3 that I can take out as a common factor, so I'll do that. And that will leave 2 times a t plus 1 in the first term, and then minus a t minus 3 for the second term. And if I clean up what's inside that bracket, I'll have 2t plus 2 minus a t plus 3. That'll clean up to give me t plus 5. Okay, so far so good. We found our first derivative. And right away I can see that there's going to be three critical numbers, one that we already knew. So for critical numbers, we know that there's no derivative at -1. So -1 is a critical number. We also know that the derivative is equal to 0 when the numerator is equal to 0, and that happens to be at 3 and at -5. So it looks like we have three critical numbers to put on our little number line. So let's do that. And going from smallest to largest, I will go with -5, then -1, then 3. And now for my choices of values for t, let's see, less than -5, I went with -6. Between -5 and -1, let's go with -2. Between -1 and 3, let's go with 0. And bigger than 3, let's go with 4. And then when I put them all into my derivative, p prime of negative 6, that turned out to be a positive number, 9/25. So we are increasing. At negative 2, it was negative 15 for the derivative. So that is decreasing. At 0, p prime of 0 was also negative 15, so we are decreasing there. And then lastly, we also have that t equals 4. When I put that in, p prime of 4 was equal to 9/25. So that's positive again, so we are increasing. So if we're thinking about what we have for our three critical numbers, I know that at negative 5, we are going from increasing to decreasing, and so we will have a relative maximum at negative 5. At 3, we're going from decreasing to increasing, so we're going to have a relative minimum at 3. At negative 1, we're not doing anything in particular. We're decreasing before it and we're decreasing after, which is neither a max or a min. But even if we were changing, even if one of these was increasing and one of these were decreasing, we couldn't possibly have a maximum or a minimum at 1, and we know that in advance because we said that at negative 1 rather, that it was a vertical asymptote. So actually, whether I had increasing or decreasing here really wouldn't matter. I still would not have a relative anything happening at negative 1. Remember, back to the beginning of the theorem, it was saying you have a critical number and the function is continuous on an interval containing that critical number. Right now, the function is not continuous around negative 1, and that's because we've got that vertical asymptote. So even though negative 1 is a critical number, it couldn't be the location of a max or a min, and that is, even if we didn't know anything about the first derivative test, just knowing the fact that there's no function there means that you couldn't have a max or a min there. So my conclusions here, I can say that we have a relative max at t being negative 5, and we also have a relative minimum, and that's at t is equal to positive 3. Okay, one last little example to look at, and this is sort of a fun one. I mean, I don't have an equation given to you at all, so there's nothing algebraic that you can really do. But even that being said, you can still find what the graph of f prime should look like. The reason is we know what f looks like, where it's increasing and decreasing. That's something we can just visually see from the graph. Which means that even though I don't know what the equation is for f of x, I know where its derivative should be positive and where its derivative should be negative. So just for this, I'm going to make a little diagram to myself up top. I can see that we're decreasing until we get to about this point. Looks like at about negative 1.5. So we're decreasing for a little while. Then we increase until we get to 0. Then we're decreasing until we get to about 1.5. And then we're increasing afterwards. So what that's telling me is in the first little interval, my derivative will be negative. It'll be below the x-axis. In the second interval, my derivative will be positive. It'll be above the x-axis. Then the derivative will be below the x-axis. Then the derivative will be above the x-axis. The other thing that I know is that at my relative extrema, at this relative minimum and relative maximum, at those places, I'm going to have a derivative that's equal to 0. So I know I can put in right away 3 points directly on my graph. I know that because there's a minimum at about negative 1.5, that f prime of negative 1.5 will be 0. Since we have a maximum when x is 0, then at f prime of 0, that'll also be 0. We've got a relative minimum at 1.5, So f prime at 1.5 will be 0. And like I said before, we're decreasing until we get to that minimum value. That means my derivative will be negative until we get to that point. So my derivative will be below the x-axis, and that's because my original function is decreasing. Then in the next little interval, my function is increasing, and that means my derivative is positive. That means in that next little interval, f prime will be above the x-axis. Then in the next little chunk, we're decreasing. So in the next little piece, my interval will be my derivative will be negative. It'll be below the x-axis. And then after we've had our minimum, my function is always increasing afterwards, which means after that point, f prime should always be positive, or should be always above the x-axis. So it looks like f prime should look something like the green graph that I've drawn. And that's sort of a nice thing you can do with any continuous function like this. Any place where we have a maximum or a minimum, those will be places where f prime will cross the x-axis. And then depending on whether the function is increasing or decreasing, in those intervals, the derivative will either be below the x-axis or above the x-axis. Below the x-axis when you're decreasing, and above the x-axis when you're increasing.